So we started off the lesson on Friday. I know I wasn't here, but was here on video, by looking at the definition of an exponential function. By the way, now that I'm here with you, I can tell you that that definition is a very limited one. Clearly, exponential functions don't have to look like y equals a number to the x. It can be more complicated than that. I think what's very important for everybody to understand is that it's exponential because there's an x in the exponent. And I believe I mentioned that in the video. That's what makes it exponential. The base of an exponential function has to have certain properties. It has to be a positive number, so it can't be zero. When I say it has to be positive, it's not allowed to be zero. But it can't be 1. And I didn't explain on the video why it didn't have to be 1. I wanted to keep the video as short and to the point as possible. But it can't be 1 because if it is 1, then your exponential function is y equals 1 to the x. And 1 to the x is 1. So the exponential function would be y equals 1. And that's not exponential. That's a polynomial function of degree 0 because 1 is just a horizontal line in terms of x. And then I showed you some examples of exponential functions that fit into this category. It's important you understand exponential functions can either be increasing or decreasing. And when we talk about increasing or decreasing, we're always making reference to left to right. As x goes up, as x increases in value, what happens to y? And in this particular graph, y increases from left to right. On the other hand, a decreasing exponential function is one where from left to right, as x gets larger in value, y decreases. And the significant difference here between these is where the base falls in that number line that we talked about. And if the base is bigger than 1, the function is growing. If the base is between 0 and 1, the function is declining or decreasing. And then we really got into, in the first example, what that base means. And this is maybe the most important part of the lesson. If the base is 2, that means y is being doubled regularly. Specifically, if the base is 2, every time x increases by 1, y is doubled. If the base is 0.3, then every time x increases by 1, y gets multiplied by 0.3. It becomes 30% of what it was. So then I had asked you in the video to add to this diagram, and this is maybe a little bit different than the one that was in your note package, but it doesn't matter. The fact that when you talk about the base value, we can put decreasing or increasing on this number line. Then we went a little bit further and we said, well, if the base is bigger than 1, we call that exponential growth. And that happens with investments with money, hopefully. Hopefully your money grows. If it doesn't, then you need to invest it elsewhere. The value of a rare painting, populations of people or bacteria, those things all increase. So that's called exponential growth. On the other hand, the word we use for exponential decline is decay. And I know the word decay kind of might mean to rot or fall apart. But in mathematics and physics, decay means to get smaller and smaller and smaller. So it's a decrease. And then what I had asked you to do, and this could be radioactive decay. Who here has taken Physics 30 already with me? Not too many. Wow. A few. So when we talk about radioactive decay, which we're going to be studying in this course as well, that's an example of exponential decay or exponential decline. Value of a car, as long as it's not a rare car. You know, I buy a truck in 2022. It's worth a certain value, so if I went to sell it right away, I could get a certain amount of money. But if I try to sell it in 2023, it's going to be less. In 2024, it's going to be less. And those things typically follow an exponential decline. I then asked you to put those words on that diagram. So it's just a matter here of being conversant in different language. Whether we talk about increasing or growth or decreasing or decay, doesn't matter. And then finally, what we said is, I'm going to skip through a lot of this, but finally what we said is, you know, things can get more complicated, and they're going to get even more complicated today. So to go from y equals c to the t up here, which is really pretty limited, and the reason it's limited is that graph will have a y-intercept of 1. If you want to start applying mathematics to things in the real world, when you talk about a y-intercept, think about this for a second. If you have something that is changing over time, that thing is y, and it could be population of bacteria, it could be value of a rare stamp, it could be a number of things, and this is time. And you want to model this using y equals c to the t, we know that the y-intercept here is 1. That's one of the first things you learned in the first couple of examples. Well, what does that y-intercept of 1 mean? It means this. It means that when x is 1, it means that when x is 0, y is 1, and x is actually time. So this y-intercept, if this is time on the horizontal axis, this y-intercept is the initial value of the thing that's changing. It's the initial value of the rare stamp. It's the initial value of the car. It's the initial number of bacteria in the petri dish. But how often in the real world do we study things that are growing or shrinking where you happen to have 1 to begin with? Very rare. Very rare. You might recall that one of the examples you did yesterday had the radioactive decay that started off at 1 gram. And I put it starting at 1 gram because you hadn't learned this yet. If you want a different y-intercept, which represents the initial amount, which we call A, then you just have to multiply c to the t by A. It's a vertical stretch. And that leads us to this equation where y is whatever is growing or decreasing, t is the time, and this is going to change today, so I'd like you to focus on this idea. It is time, but really it is how many times c has been applied. So if c is 2, that means y is being doubled again and again and again and again. So what t is how many times it's been doubled. It's how many times that factor has been applied. A is the initial amount and c is the factor by which the quantity is changing. And again, this equation will change. It will be different a little bit later today. So I hope that was... Does anybody have any questions about anything I've said here? Not assigned problems, just any general questions. Go ahead, Ian. Well, that's a very good question, and we will be dealing with that in certain cases. And it might be time, and there might be a negative there, which is going to seem strange. But let's say that I gave you the following. This is a really good question that you are likely to encounter, the idea behind this question on an exam. That you are told that, it doesn't matter what y is maybe the value of a car. And this is all contrived, so whether the numbers work out nicely or not, it doesn't matter. You buy a car, and this is the value of it as time goes on. And that means that you have the initial value, let's just say it's $12,000, it wasn't a new car. And what you have here is 1.2 to the negative t. where t is the time in years. Okay? And I want to show to you that this will correctly predict the value of the car. If I put in for y 12,000 multiplied by 1.2 raised to the negative x. And by the way, I didn't get into this in the video because it's something I would rather be in front of you to gauge your response. Where you put that negative x, whether it's inside of the brackets or outside of the brackets, doesn't matter. You don't even need the brackets. You could just go 12,000 times 1.2 raised to the negative x. Okay, but I like to do it this way. If I set up my table to start at 0 and go up by 1, if this is following exponential decline or decay, the value of the car should be decreasing, right? And if I go to my table, you can see that the value of the car is decreasing. And it's because of that negative exponent. And I want to show you a different way that we could write this equation. I could write this as y equals 12,000 times 1.2 to the negative 1 to the t. Because in grade 9 and 10, you learn that when you have, they call it a power of a power. Really, it's an exponent of an exponent, but that's okay. It's actually an exponent of a power. But you're taught that when you have a base raised to an exponent and that whole thing is raised to an exponent, that you can multiply those exponents. So if I multiply that negative 1 by the t, I get negative t. Now, it turns out that 1.2 to the negative 1 is 0.83 repeating. Can you check that on your calculator for me, please? Is that, I just need to know if that's right. It is. So, and I'm jumping a little bit ahead here, but you remember the problem you worked on with Allentown and Brementown? Well, what this is saying, 0.83 repeating is 83.3%. That number, 0.83, I'll just call it 0.83, as a decimal is 0.83, but as a percentage in terms of change, it's 83%. And what this means is that the car is being devalued by about 17% per year to be left with 83. So we can have a negative. Another way to explain what's going on here is without that negative, Ian, and this is maybe in terms of what we're doing today. Without that negative, this is what the graph would look like, and it would pass through 12,000 without the negative. If I change the t, which is really x, to negative t, it's a horizontal reflection, which turns it into what's really happening. This one is 12,000 times 1.2 to the negative t. So we can have negative exponents. Just to summarize this and then move on, just because we have a negative in front of t doesn't mean time is negative. You're still putting in a positive number for t. You're just multiplying it by negative 1 to calculate y. Other questions before we get to the assigned work? All right, so let's take a look at the assigned work. Does anybody have any questions you would like me to go over? Go ahead, Maddie. Certainly. And by the way, I think in your notes it says 12 and here it says 10. You really ought to be able to do either. But let's take a look at 12. All right, stats indicate that the world population since 1995 has been growing at a rate of about 1.27% per year. Now, keep in mind this textbook is old already, right? But let's imagine we're in 1995. And the idea here, everybody, is when we start to model exponential growth, where t is going to be the time in years, I want you to understand that t is not the year. 2011 as t equals 0. I'm not quite sure why they're mentioning 1995. It's just the point of interest. Oh, by the way, since 1995, this is what the population's been doing. But in 2011, the population is 7 billion. So that's going to be our starting point. Okay? And I would say to you that if this were on an exam, we wouldn't mention the 1995. We would simply be told in 2011 the population was 7 billion and it was growing at a rate of 1.27% per year. So the population here is 7 billion. I'm just going to put B for billion. I don't think it's really necessary for us to write 7,000,000,000,000,000. The question is, when will the population be 9 billion? So what we need to do here, y is the time in years, and t is the time in years, and y is the population in billions. You okay with what I'm communicating there? So what we need to do is come up with an equation connecting the time and the population so that we can put 9 in for y and calculate the time or determine the time. So our formula is y equals a times the base raised to the t. I can't remember now, my brain just skipped a beat, if I used b earlier or c earlier when I talked about this, but it doesn't matter. Okay? I think I used C. I did. You can see by the nods on your heads that I'm using C. So I'm just going to go with the consistent C here. So A is 7 billion. What is C? C is the rate of growth. So if you're told, and this was in the lesson, but it's a tricky thing, but it's important. Let's imagine that I have an object, a nice shiny object I'm going to sell you. And it costs a certain amount of money. But I say, you got to buy it now because tomorrow it's going to go up in price. And you go, I don't want to buy it now. You come back to me tomorrow and you say, well, I want to buy it now. I changed my mind. And I tell you it costs 1.27% more now than it did yesterday. We could figure out the new cost. Let's say it was $5,000. Let's say I had this shiny object that was $5,000 yesterday, and I'm going to crank the price up by 1.27%. Well, what's 1.27% of that? 1.27 divided by 100, because that's what percent means, is 0.0127. I multiply that by the 5,000. I'm asking for $63.50 more, which means this is the new price. But what I want to point out to you is that if you take 5,000 and multiply by 101.27%, you'll get that number. Now I'm multiplying by 101.27%. Percent means over 100. Why 101.27? Because it was worth 100% of what it was, plus the 1.27. This is Allentown or Brementown. We added it. And you get the same number. So what that means is that C is 101.27%, which is 1.0127. And now we have a formula. The formula is going to become y equals 7 times 1.0127 raised to the t. Now, you don't know how to find t algebraically yet. You have to know about something called logarithms in order for you to do it. So the only way that we can solve this is graphically, Maddie. So if we graph y equals, turn something off here. There we go. If we graph y equals 7 times 1.0127 raised to the x, we will get a graph that starts at 7 and goes up. So that helps me with my scaling for my window setting. As a student, I probably don't know how many years it's going to be. But I might start off by looking at a 10-year period or a 20-year period. I'm going to go to 15. The population is going to go up. We want it to reach 9, right? So I'm going to go from 0 to 10 here so that I get up to at least 9. There's my population. What I forgot to graph is y equals 9. Right? I also need to graph y equals 9, and I suspect that 10 or 15 years is not good enough. I'm going to have to look further in that direction. But anyway, when we do that, let's go to 25 years and go to the Calculate menu and choose Intersect. Here's my population function. Here comes y equals 9, which is really 9 billion. I guess I already did this. Intersect, enter, enter, enter. So 19.9 years. So in what year is that? Well, if 2011 was year 0, then when we add 19.9 to that, we're going to get 2011. Help me out. Was it 19.9? You get 2030 and almost 2031. So it's happening in year 2030. It's happening 9/10 of the way through year 2030. And we could have solved it, by the way, since we're asked for a year. You could have just gone to your table and looked at where the population cracks the 9 billion mark. And there you go. Now you want to be careful here. I don't think it's really that big of a deal. I don't think you would encounter it. But the question might be, in what year will the population reach 9 billion, in which case it's 2030. The question might be, what is the first year where the population is always over 9 billion, in which case it would be 2031. This is dealing with transformations of exponential functions, which is on page 5 of your Unit 5 handout. We're going to be basically applying transformations to that basic exponential function of y equals c to the x. And then we're also going to be continuing to work with exponential growth and decay. Just tweaking that general equation even more, so it's even more useful. So as a warm-up, if I take y equals c to the x, and I change it to y equals a f of b bracket x minus h n bracket plus k, what's the new function look like? Well, don't forget that f of, I'm just going to use f of x equals c to the x and say, well, what is f of clubs? F of clubs is c raised to the club. Right? That's all it means. F of pi is c raised to the pi. So f of this thing is c raised to that thing. That's what it means. So forgetting about the a out in front and the k at the end, f of bracket of b bracket x minus h will be c raised to the b bracket x minus h. This entire thing, not including the a, not including the k, is this thing. F of b bracket x minus h is c raised to that thing. So then if we multiply that by a and add k, This is the new function. And I'm going to get rid of that pink rectangle. It's just visually offensive to me. I just put it there to indicate how we got c to the b bracket x minus h. So this is the function. So you need to recognize that. You need to be able to look at an exponential function that has that appearance and say, okay, I know what a is, I know what b is, I know what h is, and I know what k is. Incidentally, can you gain an appreciation for why I would rather use the base c rather than b? Because if I use b, I've got two b's that mean different things. All right, so we're going to do a couple of questions related to that and one more exponential growth or decay problem. Describe the transformations needed to change y equals 3 to the x to y equals 2 times 3 raised to the x minus 4, then plus 15. Can you do me a favor, please, and double check to see that that's the function given in your handout, because I had to retype this morning. Okay, good. So I would like everybody to look at this. Take a minute, go all the way back to Unit 1 where we talked about A, B, H, and K, and determine the values of A, B, H, and K. So the function is 3 to the x. What are we multiplying the function by, which is the definition of a? We're multiplying it by 2. We are vertically stretching y equals 3 to the x by a factor of 2. B is the number that x gets multiplied by, but since there's nothing specifically written in front of the x, there is really a 1 in front of the x. So b has a value of 1. Remember, this goes back to the first unit. If you don't see an A is 1. If you don't see a B, B is 1. If you don't see an H or a K, those ones are 0. But H is 4 because we compare x minus H in our general transformed function on the formula sheet to x minus 4. You can see that H has a value of 4. And as I've said numerous times, K is the afterthought. K is the last thing that you see in the function. It's what's added at the very end. So what are the transformations? What's the description of the transformations? We have a vertical stretch by a factor of 2. And again, this is not a written response. I'm in teaching mode. You're in learning mode. You don't have to write it out. You can abbreviate it. There's a vertical stretch by a factor of 2. There is a horizontal shift of 4 units to the right, and there is a vertical shift of 15 units up. And are we okay with that? One of the things, I don't know why it slipped my mind, one of the things I really ought to have reviewed when I didn't is the whole idea of the asymptote. So, as an illustration, I just want to go back to the review that I did. I just want to go over the concept of a horizontal asymptote again. Maybe. Well, that would explain things, wouldn't it? Well, luckily I do have this file open already. That's one of the pitfalls. All of my stuff is in the cloud, so it's really struggling to get it. Of course. Oh, I did get it though. If we take a look at this particular function, which is an exponential growth function, and we start going to the left, we get to more and more negative values for x. Y gets smaller and smaller, but it never reaches the x-axis, because no matter what x is, negative 10 million, negative 10 gajillion, negative 10, huge number, the base raised to that will still be a positive number. So we end up with what's called a horizontal asymptote. The point I want to make here is, as soon as I saw that this function is going to be 3 to the x shifted 15 up, you should understand that that's where the horizontal asymptote will be. What we're asked to do now is sketch these functions. And by the way, your handout should say C, and when it says determine each of the following, I'm talking about for g to the x. So we can start off by sketching y equals 3 to the x. Let me put in my asymptote first. This is going to be for y equals 3 to the x, and the asymptote will be here. And y equals 3 to the x has a y-intercept of 1. And since the base is 3, every time we go 1 to the right, y will be tripled. So when we go over to x equals 1, y will be 3. When we go to x equals 2, we triple 3 and we get 9. When we go over another one, we triple 9 and get 27. We go over another one for x, we triple 27 and get 81, and I don't know if I have 81 on here. 81's not going to fit, is it? So I don't have to worry about that. I don't think it's necessary for us to draw that curve. If we were to connect the dots with a smooth curve, that would be an accurate reflection of the line. Reflection's the wrong word. That would be an accurate picture of the curve y equals 3 to the x. So we've said that things get doubled, correct? Vertically. So that means that this point, which is at 1, will be at 2. You can hardly see the difference. This point that is at 3 will be at 6. This point, which was at 9, will be at 18. And the point that was at 27 will be at 54. Everybody, I'm really not too concerned about your ability to graph an accurate, beautiful picture here. We're doing this so we can learn some things. Well, let's talk first of all about the fact that we're going to shift this 15 up. That means that asymptote is going to be 15 units up. And all of these points are going to be 15 units up. And all of these points as well will be 4 units to the right. Is my memory correct there that we're shifting 4 to the right and 15 up? So I'm going to shift this point right here 1, 2, 3, 4 to the right. And right now it is 2. Listen very carefully because there's a shortcut method here that is better. This point right now is 2 above the asymptote. So if I move my asymptote up to 15, this point will be 2 above the asymptote. This point right here is 6 above the asymptote, and it's 1 to the right of the previous point. So we don't need to actually plot every single point at every single position after every single transformation. We could have just moved the asymptote and then looked at where the points are going to be. This particular point right here is, what was it? 18 above the asymptote, so we go 1 to the right and we go 5, 10, 15, 18 above the asymptote. And I think that's good enough for a picture of what the graph looks like. We don't need to go any further because ultimately, everybody, what we want to be able to do is list the properties. In part C, it says, what's the equation of the horizontal asymptote? What's the y-intercept? What's the x-intercept? What's the domain and range? You know, I hope you remember in the first unit, sometimes you were given a graph of a function and asked to sketch on a written response the transformed graph. Remember doing that kind of thing? Or the inverse or the square root. I don't think you would ever be asked to do this with an exponential function. Okay. So what is the equation of the horizontal asymptote? Y equals 15, which you should make a note of is y equals k. It's always going to be y equals k. What is the x-intercept? There is no x-intercept. We'll get back to the y-intercept in a minute. What is the domain? Well, you can look at the graph and see that x is any real number and y is greater than 15. I want you to notice that that's y is greater than k. And I have a question for you. In terms of these transformations, will the range always be y is greater than k? And I see some of you kind of nodding, but let me be more specific. Do you think the range could ever be y is less than k? Under what circumstances, Ian, would we end up with y is less than k? Right. If a, the parameter a, is negative. So if we had this number here of 2, if it was not 2 but negative 2, then there would be a vertical reflection first, in which case the range would be y is less than that number. Yeah, Marcel. When c is less than 1, but still positive? If c is less than 1 but still positive, the only thing that will change is the graph will be going down from left to right, but it will still be above the horizontal asymptote. So just to take a look at that, this is what you're talking about, c is less than 1, but the horizontal asymptote is still the x-axis and the graph is still above it. So if I shift this up or down, it will still have a range of y is greater than k. The only way you can do it is to reflect it vertically with a negative a. Yep.
What if the base was negative?
You can't have a base of negative. And I would like to get into a discussion with you about that, and I will at the end of this lesson, because it's very interesting if the base is negative. But the base cannot be negative. By definition, the base must be a positive number, not 0 and not 1. If the base is negative, some weird, wild, wacky things start happening on the graph. And I would like to talk with you about that after we're done today, because I think it is interesting. Okay, now how do we find the y-intercept? Well, the y-intercept, by the way, we never used this point. The y-intercept is where x is equal to 0. So the y-intercept, I've got some space up here. The y-intercept will be equal to two times 3 to the 0 minus 4 plus 15. It's going to be a number just a little bit more than 15. I mean, I'll go in decimal form and then I'll work it out in as a fraction for you. When you work it out in decimal form, it's this number, 15.024. It's just a little bit above 15. I can't even begin to imagine how I would plot that point on my graph. It's going to be over here someplace. Right? The y-intercept is going to be someplace over here, very, very close to that 15 for the horizontal asymptote. By the way, as a fraction, and you can let me know if you're getting the same thing, 1217 over 81. When you put that into your calculator, 2 times 3 to the negative 4, then plus 15. So 1217 over 81. Let's take a look at the next example. What are the So we're not asked to graph this. First of all, you should see that there's a vertical reflection because A is negative 1/2. I'll put that on the side here. You should see that there's a vertical stretch by a factor of 1/2. The reason it's a vertical reflection is because A is negative. There is a horizontal stretch by a factor of the reciprocal of B. B is 1/5. And there is a shift of 5 units down because K is negative 5. I should have asked, is this the same function in your note package as I've typed up here? Okay. So the vertical reflection and the vertical stretch are a result of A being negative 1/2. The horizontal stretch by a factor of 5 is a result of B being 1/5. And since K is negative 5, the graph is shifted 5 units down. Okay. Well, what's the domain? If you take this graph and you do anything in the world to it in terms of A, B, H, and K and shift it and reflect it and stretch it, not in that order, the domain is still going to be any real number. It has to be. So X is any real number here. The range, the graph will always be above the horizontal asymptote or below the horizontal asymptote. And since the graph was shifted 5 units down, the horizontal asymptote is at negative 5. Now the question is, that's fine. Yeah. The question is, will it be y is greater than that number or less than that number? Reagan? Less than. And what's the reason for that? Right, there's a vertical reflection which tipped the thing below the horizontal asymptote to begin with. By the way, there's never an equal to on that inequality, ever. The x-intercept. Well, will this have an x-intercept? If the horizontal asymptote is below the x-axis, which it is, and the graph exists only below that, there will be no x-intercept. Now, sooner or later, you are going to encounter an x-intercept. And we'll worry about that when the time comes. The y-intercept is found by putting 0 in here. So I would like everybody to put 0 in for x and use your calculator. We'll see you tomorrow. Use your calculator to calculate what the y-intercept will be. I want to say negative 5.5. Because 3 raised to the 0 will be 1, so you have negative a half minus 5. What is the equation of the horizontal asymptote? Y equals negative 5. And we're done. Any questions with that example? Okay, one more thing to look at. I promised you, not like it's a big surprise, but I promised you that we would take the exponential growth decay formula, which started off this way. Then we changed it to this because x is time. Then we changed it to this because the y-intercept isn't always 0, and I said we would change it further. Unfortunately, when we look on the formula sheet, they change the base from C to B. Okay? So I want to point out to you that in your notes it says for exponential growth or decay applications, we use the following formula, and it always works as long as there are no translations. So how can I put this? This formula that's in the box right there on the screen and in your notes has nothing to do with transformations. This has nothing to do with the first two examples we looked at. When you go to your formula sheet, I think I have one open here. When you go to your formula sheet, nope. And you look on the left-hand side, there is something called growth and decay formula. It's just above the general form of a transform function, and there it is. And they use B for the base. So we have to get over it. We have to just deal with it. Okay? But you'll notice that something else has been added. It's no longer just raised to the t, it's raised to the t over p. Now, before I get to all of the details, I hope you recall that I made a big deal out of the exponent being time, but it was really how...
Please excuse the interruption. It looks like the internet is back up and running. Thank you.
I made a big deal about the exponent being time, but more specifically, it was how many times the base had been applied, right? So if you used the exponent of 5 and the base was 2, then things were doubled 5 times. So look at what I'm telling you P is. P is the period of time required for the quantity to change by the factor of the base. So let's say that P was 2 minutes. Let's just say P was 2 minutes. So we're dealing with a question that says maybe I better not use 2. I'm going to go with 3 minutes. We're saying that maybe we're dealing with a situation where bacteria is doubling every 3 minutes. Every 3 minutes. Which would mean if I said doubling, B is 2. If I told you the time was 15 minutes, think about this. If I wait 15 minutes and it's doubling every 3 minutes, how many times does it double? 5, right? And you can get 5 by taking t, which is 15, divided by p, which is 3. That's why we have t over p now. Some more details to this? Well, not really additional details. B is the factor by which the quantity changes. So in the example that Maddie had asked about, since the population was going up by 1.27%, B was 1.0127, 101.27%. T is the time, and A is the initial amount. So we have one last example here. We have a radioactive element called americium. It has the symbol of Am, and it's used in smoke detectors. If you've taken Physics 30, if we take our Geiger counter and you go against a smoke detector, it will tick away. And if this were a Physics 30 class, we would explain the significance of that and what's going on. But turns out you've got a radioactive isotope or source in your house. And the half-life is approximately 432 years. So what you need to know now is what this means. It used to be in a Math 30 class, they would always tell you what it meant, and now they're stopping to do that. They're not doing it anymore on exams. It means it's halved every 432 years. And we use the symbol A for years. It means annum. What does that mean? It means that the base is 1/2 and P is 432 years. If you look on the previous page, P is how long it takes to happen, and B is what happens. A is the initial amount, which is 200 grams. Well, 200 micrograms. So what's the equation for the exponential function that describes the amount of the radioactive isotope that remains? I'll be right back. Sorry about that. All we have to do is put those numbers into that formula. The formula is the amount of americium 241 that remains is the initial amount times the base raised to the T over P. So we'll have Y equals 200 times 0.5 raised to the T over 432. And that's it. I didn't ask anything else here, but I could very easily ask you this question. And it would be almost identical to the one that Maddie asked about at the beginning. If the smoke detector needs to be replaced when the amount drops below 190 micrograms, how many years is it good for? And what you would have to do is sketch, well, use your graphing calculator to find the point of intersection. And that would be the answer to the question. By the way, it would be a large number of years because the half-life is so big. A whole variety of different questions dealing with some applications. 11 and 12 are applications, and the rest of it deals with transformations. So everybody can get started on that, and I will hand back your exams so you can take a look at them. If you are looking at rewriting, rewrites would be Thursday of this week and Tuesday of next week. Same thing as always. Don't just speak to me verbally. You need to send me an email communicating your desire to rewrite. If I don't have a record of an email, it's not going to happen. So get to work on those. I will get your exams back to you and come around and help you out.